Hello, my name is Camila. I'm a postdoc at INPE, Instituto Nacional de Pesquisas Espaciais in Brazil. The work I will present here comes from the joint effort of the BIM collaboration and show the first results evaluating the potential of the Bingo telescope, of the future data of the Bingo telescope in measuring the BAO signal. So the BAO has its origin in the primordial universe and is a result of the competition between gravity and the pressure of radiation. So this competition generates this wave of matter, and the BAO scales corresponds to the distance this wave of matter travels until the recombination when the radiation and matter, they decouple. So due to this previous coupling, the BAO signal appears not only in the fluctuations of temperatures of the CMB, but also in the distribution of the large scale structure. So we can see here in the angular power spectrum of the CMB, a clear signal of the BAO feature here. And also in these other two plots from large scale structure, we can see the P of K here, the power spectrum, the matter power spectrum with the BAO wiggles. And also we can see here on the left, the 2-point function showing the presence of the BAO peak with an axis of probability of finding two galaxies separated by this characteristic scale. So how we usually measure the BAO signal? We can, for example, use a weakly model-dependent approach using an empirical equation to fit your data points, where you find fit and find this theta position of your BAO peak. Also, another approach is a template-based method, where you fit a template constructed based in a given cosmology. You fit it to your data. So this is the case we are using now for this analysis of bingo simulations. And the idea here is to find what we call the shift parameter. I will show you later, but this is a parameter that quantifies how the BAO peak measured from the simulations or from the data, how it shifts with respect to the position expected from your model. So bingo is a telescope that is being constructed in the state of Paiva in the northern of Brazil. It will have a primary dish with 40 meters diameter and a secondary one with 34 meters with 28 horns in its phase one, like we see here in this picture of how bingo will be. It will cover 6,000 square degrees of the sky with a resolution of 40 arc minutes in this range of frequencies, which corresponds to a redshift range from 0.13 to 0.45. Here we see the region that bingo will observe. And here, this region that we already removed from our analysis, which corresponds to the region that is more contaminated by foregrounds. Bingo will do a tomographic approach, so it will observe several redshift ranges. We can define this as we wish, but it will probably be based on how well we can perform the component separation, foreground removal. So for our analysis, we consider bingo-like simulations where we include several observable, characteristics of bingo observation. So we consider the same sky coverage, which we show here in these two lines. We also include the thermal noise, foreground residuals, and also the bingo beam. For the 21 centimeter signal, we use two different types of simulations. We use the ones constructed using the Flash code, and we also use a smaller set of simulations based on anybody simulations. So we consider here for this analysis two types of clustering measurements: the angular power spectrum, taking into account the partial sky coverage, and also the angular correlation function. We see here in these two plots the position in terms of multiples and in terms of theta scales, that the BAO signal appears in each case for two different beams in the border of our redshift range. So we construct the model to fit the measurements of the CLs and W of theta in the simulations like this. First, we construct this P of K, this template of the power spectrum using the linear power spectrum and the power spectrum calculated without the BAO wiggles. From this P of K, we can calculate the CLs and use it here in this model. The same for the W of theta, we use this same CL and relate it to the W of theta, and then use it here to construct this model for the W of theta. So to fit this model, we use a maximum likelihood estimator. And our main free parameter is this alpha parameter, the shift parameter I just mentioned, which estimates this shift between measurement and the model of the position of the wiggles or the peak. And B and AI are free parameters fitted to each of the redshift beams individually, while the alpha parameter is fitted to sets of redshift beams. For example, here in this first results, we see a histogram of the alpha parameters fitted to the first 10 redshift beams of each Flask simulations. So we have one alpha parameter for the first 10 beams, one for the intermediate 10 beams, and one for the last 10 beams. And this is done for all the Flask simulations. And from this, we have this histogram. Here in the second row, we can see the histogram now for the significance of these alpha measurements. So we can see in blue results obtained analyzing clean simulations, only including the beam effect, while the red one show the results when we include the white noise, and the green one including also the foreground signal, the foreground residues along with the white noise. We can see that the effect that has the larger impact is the white noise, where we see here a larger sigma 68, which means a larger dispersion of these histograms compared to the blue one. And we can see that differently from the white noise, the inclusion of the foregrounds in the green lines do not seem to have a greater impact. So we can have this conclusion from both lines from these angular correlation function results. And also from the angular power spectrum results, you can see the same behavior with a larger impact of the white noise on the higher redshift. It happens especially because the BAO wiggles, the BAO feature appears at smaller scales at higher redshifts. Scales that are that starts to be dominated by the white noise, by the thermal noise. So this is the reason why at higher redshifts we have this larger impact of the white noise. So just to summarize here what kind of analysis we have been done here, we consider different bindings of this range of redshift. We've been this range linearly in frequency, linearly in redshift. We also consider different ranges of redshift to fit the alpha parameters and the other parameters. And we also perform several robustness tests for changing the binding of multiples and this binding of theta angles when calculating the cluster. So these are a summary. This is a summary of the results from the W of theta, and this in red here we see the results from the fiducial configuration, where we chose here the one with a binding in theta of 0.5, and this I here corresponds to that AI in the model, because we tested also different parameterizations in that model. So we can see here the average of alpha estimates from the flash simulations, the average error from each of these fittings, and here the dispersion of the alpha estimates, the 68%, and also the standard deviation here. We can see also the percentage of maps that actually has a BAO detection with significance. And here, in this column, we see the significance of this detection. So if we compare these results with the results of the CLs, we can see that the CLs has a smaller bias on the alpha parameters that we expect to be around 1, while the W of theta has a larger significance at these smaller redshifts. So just to summarize here our main results and conclusions, we see here that the two clustering estimators show the best results at higher redshifts, while they present different sensitivities to each redshift range, just like I just showed you. And the results from intermediate and the higher redshifts also show that these redshifts are more promising to measure the BAO scales, even with the larger impact of the white noise at higher redshifts. Also, we evaluated what happened when we include the noise. We see that it has the larger impact when compared to the foreground residuals, which seems to have no significant impact on our analysis. And just to finish here, I would like to emphasize that even including these realistic systematic effects, our results, our analysis show that bingo has the potential to detect the BAO feature in its redshift range during its phase 1, which is the 5 years of operation. So thank you for watching, and please feel free to send me any questions, suggestions, and comments about this work. Thank you.